Another very powerful environment for controls applications is Octave. Octave is also an open source software package, can be downloaded and used on almost all the operating system platforms. It has a powerful set of toolboxes, and especially for controls, you will see that Octave is very strong in numerical computation and it is well suited for controls purposes. We shall be studying this Octave and see how we can use it for designing our controllers. Let me now open Jupyter, and you will see that Jupyter is open in the browser. And if I go to the right hand portion here, the new, if I click here, you will see that we have a Python kernel. We would like to also introduce an Octave kernel here. In such a case, then the Jupyter notebook can be used even for Octave programming. So you will have an interactive notebook which can handle both Python scripts and also Octave scripts. Of course, Octave itself has its own independent environment, its own independent IDE, which we will also explore later, which is quite powerful. But Jupyter is good for documentation, as we have seen earlier while using Python. Let me open up the command window and install two things. One is I have to install Octave, and the other one is to install the Octave kernel for use with Jupyter. So first I will install Octave. I have already installed Octave, so therefore you will get the message saying that it has been already installed. So let us check that out. So you see that Octave is installed. Now next, let me install the kernel. I'll use the pip install Octave kernel. So the installation is completed, and we can now go back to Jupyter. We can now restart Jupyter and check if Octave kernel has been installed. So let me go back to the applications window, click on Jupyter, it will get restarted. And now when I click at this point, you see that you have Octave and Python, both are there. So you have the Octave kernel and also have a Python kernel. So Jupyter Notes can be used as an interactive scripting program, documenting program for both Octave and Python. So let us see how we go about doing this. Let me go to the file that we used to normally use for this course, control examples. Recall that we had created a set of examples for learning Python. So I will open that. So this is the file that we had created while learning Python. So we will use this same set of examples with Octave. So let us try to learn Octave using these same examples and how it would look like in this Octave environment. Let me change the title to Learning Controls through Python and Octave. So let us include Octave also. So you have this, and after below this cell I will insert one more cell, and in this cell I would like to include this Octave scripts. Observe here, this particular cell is indicating that it is going to look into the Python kernel, but we want it to look into the Octave kernel for compiling. So let us go to this kernel, change kernel, and I will change it to Octave. So this particular cell will use the Octave kernel for compiling, whereas this cell, when you compile, you have to choose the Python kernel. So right now I have set it to Octave kernel because that's what we are going to do the programming, script programming. So just like here, you have to load some modules. So some required modules to load. So in Octave we load the modules. We use package load the control package. So the control package is available in the Octave repository. It would have got loaded, it would have got installed when you installed Octave. Another package that is of use for us, package load signal, the signal processing toolbox, the control toolbox. These two are definitely needed. So there is a third package which I would like you to load. That's called LU control. This is not coming from the Octave repository. This LU control is a collection of tools specific to controls that I have collated based on the work from the students and the lab work that we have done. So this collection is a useful set of tools which will be helpful for doing the controls development. So you need to load these two. But LU control, this third one, LU control has not been installed in your Octave. So we need to install that first from a package. I will tell you how to do that. So before I execute this, let me insert another cell above. So here, before I do anything else, I would like to do once a package install of LU control 2.0 tar.gz. So this is the LU control package. Where have I located this? It is in the directory, the same directory where we, so this one, the same directory where we use this learning Python. I have kept LU control -2.0.0 tar.gz. I will make it available for you to download this. So this we are going to load, install in this particular Octave machine having this Octave. Now let me go back to this, and this, let me first execute, because then this will install. This is only once, you do it only once. So let me run that. So that would have got installed, and this you can load every time you enter the Octave environment. So let us run this also. So all these modules are loaded into the environment. I will now continue with this part of the program, that is defining a transfer function. I will use the same transfer function, but how does it look in Octave? So let me comment. We'll comment this. Define the transfer function. So I will use num, the numerator part, polynomial, and I will end each line with a semicolon as a delimiter in Octave. If you do that, then the output will not be displayed onto the console. But if you don't give the semicolon, every line output is displayed onto the console. So in order not to clutter up the console, it is better to give this delimiter. So I will use that same denominator polynomial as before. So for this last statement, I am not using the semicolon delimiter because I would like to see what is the output of this statement. I would like to see what is the transfer function. So now let us execute this cell. So let me run. So when I run here, you see that transfer function of C is 1 by s square plus 0.5 s plus 2, which is the same as that we had executed during the Python scripting exercises also. So this is the continuous time model. So this is how you would enter the transfer function. Now let us plot the results. So here we had set the time axis and then used the matplotlib module to plot the results. Here it is pretty much easier. So what we do is, let me delineate this, and then I will use the step function. Step C. That's it. This should give us the plot, and I can give the x and the y label. Let's say x label, and give the same thing, time in seconds. Then y label. See that I am using delimiter, semicolon, magnitude, and title. Here it is much simpler to plot and give the labels. Step response. So you have it here. So let me run this. We will run this, and you see this is the step response. You have the y label magnitude, x label time. Let us compare with this. Let me execute this also, but let us convert this to first another change in the kernel, Python kernel. So now the kernel is Python. So I will execute this as a Python script. So let us run this. So you see this is the transfer function 1 by s square plus 0.5 s plus 2. And what we have executed using the Octave script here is also the same one, same transfer function and similar responses that you have seen here. Okay. Let me now clear all the outputs. I'll go to cell, all outputs I will clear, and I will again change back to the Octave kernel. Go to the change kernel. I will pick the Octave kernel, and let us now take the second example where we would like to see how we discretize the transfer function and plot the discrete step response. So we saw how we can do it with Python. The same system as we have defined here, we will take it up and then use Octave scripts and see how we can do it in Octave script. So I will insert a cell below, and it is an Octave, and I will pick the same package, load, copy, load controls, load the package signal, and load the package LU control, which is the local package that we installed. Now defining the transfer function, I will use the same transfer function. Let me define the transfer function. So the continuous domain transfer function, numerator, polynomial, is 1, the denominator polynomial is 1, 0.5. So the same transfer function that we used for the other examples. Now one more variable, ts, the sampling time. So I will use the same sampling time that we used for the Python example above. ts is 0.5 seconds. Now the continuous time system is this. Using the TF tool, we pass in the parameters, the numerator polynomial and the denominator polynomial. Then for the discrete time system, we will use, there is a continuous to discrete time conversion, but the control toolbox of Octave still is not ready. It is that is still not done. However, we can use the control to continuous to discrete time transfer conversion of the LU control toolbox. So I will use my C to D. Numerator, I will pass the numerator, the denominator polynomial and TS. So this will give the numerator polynomial and the denominator polynomial of the discretized system. Now I can obtain the discrete time system TF. I will give NZ, DZ and TS. So this is what I will be passing on. So using this you can plot the discrete. We can see what do you get. I will remove this semicolon so that I can see the continuous time system and the discrete time system and run. So this is the continuous time system, 1 by s square plus 0.5 s plus 2. So with a sampling time of 0.5 seconds, this is the discretized transfer function. So next I will plot the step response. So you can do it either this way, you can plot step and pass the discrete time system. That's it. This should give you the step response. Let me run this. So this is the step response. Of course, you can fill in all these variables, the x-axis, y-axis, and the title in the same manner as we did previously. You could also plot the continuous and the discrete time as subplots as we did for the Python script. So how do we do subplotting? So let me show that. I will remove this line here and say subplot. So you have two subplots and this is the 1, 1 subplot. Step. So C, which means the continuous time system. So let me first plot the continuous time system. X label. So this is time in seconds. Then the Y label. Magnitude. Then title. Discrete step response. So this is the first subplot. Then the subplot, the second one. So here I will take the step response of the discrete system. And you can fill in the label, X label, Y label as necessary. So right now let us leave it at this, and I will run this command. So when I run this, so you have the continuous time system, the discrete time system, the continuous time step response, and the discrete time step response. The title and the labels have not appeared. There is an error. Okay, I have typed it, not typed it properly. So let me type that, correct that spelling mistake, label, and then rerun that. And now it is right. You have the discrete time step response, magnitude, and all these things. So this way you can get the discretized version of the continuous domain transfer function even in the Octave scripting. So it is pretty simple to do that. And next we can look at an example of a Bode plot. So we again saw how to do the frequency domain plots in Python scripting. We will use the same plant, the same transfer function, and try to see how we go about getting it in Octave. Let me insert a cell below, and I will start entering the script for frequency response here. So let me put in the required packages. So package load control and package load signal. These two packages are needed. So I will include them, and then let me define the transfer function. The transfer function is the same thing. I'll say the numerator polynomial, the denominator polynomial, and the system is using the TF function, numerator and the denominator polynomial. So you have the system, and let us define the x-axis. So the x-axis is omega axis log space from 10 to the power of minus 1 to 10 to the power of 2. So this spans 3 decades. And now Bode. So Bode, system, and omega. These are the two parameters that you will be passing, and we can now run the cell and let us see the results. So this is how the Bode plot results will be. So you see that it is starting from x-axis is starting from 10 to the power of minus 1 as 0.1 to 1000. And this is the magnitude plot, and the one below is the phase angle plot. So it's pretty simple getting the Bode plot. So if you give the discrete transfer function here, or the discrete system, you will get the Bode plot of the discrete system. You will have to accordingly choose the omega axis such that it is it observes the Nyquist sampling rules. As I mentioned earlier, one need not have to use Jupyter nodes. You could also use the very powerful Octave environment. Let me click on this application. So once you install Octave, you will see here at the bottom this Octave environment. So you can adjust. So this is the working environment of Octave. Let me clear the screen. So you have a command window. So if someone is familiar with MATLAB, it is very similar. You have a command window. This is the workspace where you will execute all your interactive commands. You have here an explorer where you can explore your folders and files. You have the workspace variables which will appear here as and when you are typing in the variables and assigning values to them. And then you have the command history, which will give you an idea of the history of commands that you have used. So this is an interactive IDE, very powerful, and you can do a lot of things with this Octave IDE. So it is not necessary that you need to use Jupyter, because especially if you want to do interactive, so you have a plot where you want to do interactive actions like picking out a pole or picking out the gain in a root locus plot, it is better to use this Octave environment. So in the command window, you can type in the variables interactively, like for example, you have the numerator polynomial or the denominator polynomial. You can type in as vectors, and then it is a kind of an interactive environment. But we would like to scripting. So as you are giving in the variables, you see here that in the workspace, variables get assigned and then they get declared and assigned automatically based on the commands that you give. Let me open a text editor. So I open a text editor here. Let me resize the Octave such that it is next to next like this, where you can see both the text editor on the left and the Octave IDE on the right. So now let us write a simple script, small script on the left in the text editor to display the root locus of a system. So this will become our basic brick for doing the root locus study or root locus design for controllers. So let us do that. So let me the required packages. So package load control, package load signal, and package load LU control. So these are the three packages that we are loading into the system workspace, Octave workspace, and then now we will define the transfer function, the same transfer function which we used earlier. Define the transfer function. So the numerator polynomial, pretty simple, is 1. The denominator polynomial is as shown below here. And let us plot the root locus. Now this is the transfer function, and plotting the root locus is simple one-step command. So in Octave, there is something called rloc find. But in the control system toolbox available in the Octave repository, rloc find is not completed as yet. So I will use from the LU control toolbox, which I have loaded, my rloc find, and you pass on the parameters, the numerator and the denominator polynomials. So the root locus, this will give you the root locus. So let us do this. There are two ways. Well, let us first save this. I have saved this file as octave_rlocus.m and I've saved it in the controls examples folder itself, which we are normally using for all the other files. There are two ways in which you can execute this. One is brute force. You just copy all the script lines, take your cursor to the right on the Octave IDE, the Octave Environment window, and then paste, and then press return. You will see that the script lines, script codes execute. So you see here that you can put in the grid. You have a figure window here. You have the pole locations. You have two poles, complex conjugate poles here. Left off of the zero line, which means they are the poles are stable. So this is the root locus of this continuous domain transfer function as we have seen here. This. Now, what does this my rloc find do? Firstly, it plots the root locus, and secondly, look at the cursor. Cursor is having a crosshair. You can place the cursor and click on any part of this root loci, and any of the root loci. So it will give out the k gain value at that point where you are keeping the cursor, and also the closed loop pole location. So if you take, for example, this particular root loci, every point is a closed loop pole location, as we have discussed earlier, corresponding to a particular value of gain k. So when you click here, for that same value of gain k, which is at this point, at all other root loci, in this case one more, corresponding value of gain k, it will pick out the poles and display. So that is what k and p is. K is the gain, it will display the gain, and p is the closed loop pole locations at that value. So let us say, for example, here we are having y-axis 2 and the real axis around minus 0.25. So let me click there. So the moment I click there, you see here gain at that point is 2.08 something, and the closed loop pole locations, you have two complex conjugate poles, one on this which is minus 0.25 and plus 2i, minus 0.25 and minus 2i. So you get two closed loop pole locations. So this can be used for actually completing the design of your controller through the root locus design. So this is the basic functions that you will be using for the root locus design. We will now use these two, this and one more, which I will present to you for looking at the root locus plots and getting out the gain and the closed loop pole locations. Now this is what you have seen here. You can also directly execute this file. So if I go in, let me clear all the variables, clear. So let me go into this location. So you see that Octave rlocus, this is the one which is saved. So I am in that particular path. So let me run that, Octave rlocus. You don't have to give .m. So you will see that it will execute, and this is the plot of the root locus. Okay, so now this is the continuous domain root locus plot. Now what do you do for plotting the root locus on the z plane? So that is what we will see next. So let me close this and introduce what I would do for z plane. So now let us say you have nz dz output. So my C to D, my continues to discrete. So what I will pass? The numerator polynomial, denominator polynomial, and the sampling time Ts. So here I need to define Ts. So let's say 0.2 seconds. So now here I have nz dz of the discretized transfer function. So let me pass nz and dz. So before I do my root locus, I will have to indicate that it is a z plane. So the plotting has to be done on the z plane so that you have a background which is z plane. So for that, a useful function which we have actually prepared and located in LU control is myZgrid. Just that. So myZgrid just gives you the background which is the z plane. So now let us execute this. So let me save that and execute this. So in this one I will run that Octave, so it will convert it into the discrete domain. So you have the background, you see this is the z plane, the unit circle, and you have the z plane constant damping ratio low size. You have two poles here and 1 0 here, as we have seen for the same example even in Python, similar root locus plot. So here too I can click anywhere here, let us say, and I will get the gain value and the closed loop pole value. This is within the unit circle complex conjugate poles of these two root loci. So this is how you would do for a discrete transfer function. Now using this basic concept, let us develop the complete program for designing a controller using the root locus method.